In the previous video I showed you the dining philosopher's problem. In this video we are going for the first endeavor in modeling the problem using Petri nets. So what you see here is a Petri net. It's composed by these bars and these circles. The circles are called places and the bars represent transformations. So what's the idea? The idea is that places contain resources represented by these tokens, and transitions take resources from inbound places and spit out resources in outbound places. So you can see that in this model all the elements of the naive dining philosopher's problem I introduced in the last video are still present. You have the four philosophers, there are the four colored squares, and you have the four cutlery pieces. You have a resource in each cutlery piece place because we know that in the beginning all the forks and knives are on the table. You see that the difference here is that philosophers now are not just like atomic things, but they are basically systems themselves. Each philosopher has some internal state that can be in different states that represents which kind of task has to be done by that philosopher. So at the moment all philosophers are basically thinking. Suppose that green philosopher decides to eat. So what green philosopher will do is will consume this token and this token. Both tokens have to be consumed if they're in the input of a transition, and we'll spit out a token here. So you see that now the token representing the fork disappears because the fork is being used by the green philosopher. Now the green philosopher, after having picked up the fork from his left side, needs to take the knife from his right side. Now this transition can fire because there is a resource here and a resource here. So the transition fires and this is what happens. Now the philosopher eats, and when he's finished eating, automatically all the tokens are put back in place. You see that in this way we can model the concurrent behavior because, for instance, if this philosopher decides to eat and so picks the knife, then this philosopher here can't do much because this philosopher can pick the fork, but now the philosopher needs the knife and the knife resource is being used by red. So this philosopher will have to wait for red to finish to get back the cutlery tool that he needs. And also we still capture the deadlock behavior we had before, that is basically expressed by this situation here, where each philosopher takes the cutlery tool on their left side and now no one can do anything. The system in fact doesn't have any kind of other transition in these states that can unlock the situation. All these transitions are waiting for a resource that will never be freed again. This is problematic, but the formalism of Petri nets can help us modeling further our problem so that these situations like deadlocks can be avoided. This will be covered in the next video. Thank you.